This is a derivation for arithmetic series, the equation that allows us to add up the sum of the terms in a sequence. So instead of commas here, we have addition signs between a series of numbers, all of which are counting up by 1. So in this case, we're just adding the natural numbers beginning at 1 and going up to 10. Famously, when Gauss was in elementary school, his teacher thought, thought of giving the class an assignment that would take a long time, asking them to add up the numbers from 1 to 100. And Gauss came back a couple of minutes later and told the teacher that the sum of the numbers from 1 to 100 was 5,050. Now, for most folks, when we're asked to add up, a series of numbers, we would say, okay, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, etc. But of course, if we're counting up numbers all the way to 100, that would be a long and tedious process. We have a much better way of calculating the sum of numbers that follow an arithmetic series. The key is to think about how the first number and the last number will add up to the second number and the second last number. For example, if I took the 10th term here, which is 10, and added it up to the first term, I would get 11. 1 plus 10 is 11. If I added up 1 before it, if I took the 9 and added it up to 2, notice how we would also get 11. If we take the 8 and add it to the third term, which is 3, that gives us 11. And the fourth last term with the fourth term, which is 7 and 4, also gives 11. Lastly, we have 6 and 5, which gives us 11 as well. So basically, if we wanted to add up all of the numbers from 1 to 10, we do 1 plus 10, 2 plus 9, etc. And we get basically a rectangle with a base of n over 2. Because we've stacked up the 10 with the 1, we only have half the n values, but we've added up t1 with t10 and t2 with t9, etc. on this column. So we're basically adding up t1, the first term, with the last term and everything in between, which gives us the exact same numbers. We don't need to say t2 or tn minus 1 because they give us all the same value. t1 plus tn will give us the same. And so the equation, quite simply then, for the sum of the numbers in an arithmetic series is just n over 2 times the first term plus the last term. Now, let's say we didn't know what the last term was. If we wanted to import our equation for an arithmetic sequence, which is tn equal to t1 plus d times n minus 1, we can plug that into this formula and come up with the sum of the numbers in an arithmetic series if we didn't know the last term, but we knew what the common difference was, d. So if we did this substitution, we would have Sn equal to n over 2 times t1 plus another t1 plus d times n minus 1. If we add up those two T1s, we'll get the sum of n terms equal to n over 2 times 2T1 plus d times n minus 1. And those two equations are two different forms of the equation for arithmetic series. Of course, if we were to add up these numbers and plug in what is S10 going to be, well, S10, of course, is going to be 10 over 2. And then the first term is 1. The 10th term is 10. So S10 is equal to 5 times 11, which is 55. What about Gauss? S100, the sum of the first 100 numbers, we have 100 over 2 times 1 plus 100, which is 50 times 101, and 50 times 101 is 5,050, like Gauss said. And this is how he solved it so quickly.